Hi, my name is Dick Larson, and I'm a teacher at MIT in Cambridge, Massachusetts. That's the Massachusetts Institute of Technology. And I'm delighted to be with you today, and thank you for sharing a few minutes of your time with me. I'm about to talk about a very interesting project that we're doing jointly with several universities and high schools in Pakistan, in Jordan, and in the greater Boston, Cambridge area in the United States. The project is called Blossoms, Blended Learning Open Source Science or Math Studies. And you can see the logo of the Blossoms project on your screen right now. And this talk I'm giving here today is co-authored by my Blossoms colleague, Mary Elizabeth Murray. And either one of us is available to answer email questions and these sorts of things, and our emails will be shown on the bottom of the screen momentarily. Okay, so what is this about, you might say? Well, it's about exciting young people in high school, young boys, girls who are teenagers, about pursuing science and math, first of all in their studies, and then later on, perhaps pursuing this in college and then in careers, in engineering, in science, and mathematics. These are the careers of the 21st century. So that's what we're talking about, blended learning, open source science or math studies. Now, you might say, wow, that's a lot of words. What does all this mean? Well, today in the next few minutes, I'm going to show you what this means. We had the Blossoms logo and some blossoms coming out of the ground in a recent MIT webpage over a weekend early in January 2009. And basically, here's our thought. And those of you who are accustomed to the virtual university here in Pakistan know this. Because with modern telecommunications technologies, sometimes with computers also, we can get quality education to anybody, anywhere. So in the future, we shouldn't think that a child's educational opportunities are limited by where they were born or the wealth of their parents. Okay? So that's the dream. The dream is with e-learning and with technology, it could be as little as videotapes and televisions. We can get quality education to so many young people that in the future, their aspirations, their God-given talents can be fully matured and realized later on as they become adults in their careers. So there's a famous Chinese saying that if you plan for a year, plant a seed. If you plan for 10 years, plant a tree. But if it's for 100 years, teach the people. And when you sow a seed once, you reap a single harvest. When you teach the people, you reap 100 harvests. And that's Con Chung from China from many years ago. And that's a little bit about what we're talking about here, is investing in education of one's people is really an excellent long-term investment. So what is it about Blossoms that we're doing? What is this thing? And I get excited, so I have to stand up, because when I get excited talking about Blossoms, I have to stand up and talk about it. And basically, there's a movement on now that started in this decade, in the first decade of the 21st century, thinking that education is not a privilege of those who are privileged, or those who have money, and those who are born in the right circles, but it's a right, that everyone should have a right to quality education and access to education, and much of educational opportunities that are available should be given out free of charge. Why not? And I'm very proud that my institution in Cambridge, Massachusetts, MIT, was one of the leaders in this in the early part of this decade of the 21st century, where we said, okay, MIT teaches 1,800 courses at the undergraduate and the graduate level. Why not take all the material of those courses and put it on the World Wide Web for free, and let people worldwide have access to that and use that, translate it into local languages, and use it in your local curriculum. So that was the beginning, that was the major beginning of the open educational resources movement, which started in the early part of the 21st century. Blossoms is an extension of that. Blossoms is part of the open educational resources movement. It's funded not by governments, but by private foundations, the Hewlett Foundation in the US and the Sloan Foundation. It's also co-funded here in Pakistan by the virtual university that you're watching today. And we're very obligated and thankful to Dr. Naveed Malik, who's the rector of the Virtual University, for providing this opportunity and for supporting Blossoms here in Pakistan. So the idea is to develop a whole set of interactive video modules for high school classes that are studying science and math. And the model of this is not a student sitting down in front of a computer and learning just in front of a computer by himself or herself. The model of this is that these students would be in their regular classroom in a public or private high school with their regular in-class teacher. And what would they need? Do they need a computer? Not necessarily. Do they need internet connectivity? No. Technologically, the needs are modest. All we need is what you're watching right now, is a television. Doesn't have to be a new television, doesn't have to be a flat screen television, and a VCR. So these video modules that we're creating can be created and put on videotape and sent to these high schools here in Pakistan, our partner country in Jordan, in the Middle East, and also in the greater Boston area in the USA. And the idea is that these video modules would be designed to be interactive with the class and with the teacher and expand upon the usual government-mandated curricula in different ways. Excite the students about math and science. Get them committed to it. Say, oh my goodness, this mathematics that I'm learning applies to the real world. I can see applications. I can see if I keep studying hard and learning this in fundamental ways, I could go to college or university and maybe have a career in this. Okay, so that's the idea. Ultimately, if those of you who have been to YouTube and see that people can load up videos, we're thinking of a moderated, quality-controlled YouTube for educational purposes in high schools. That ultimately, if this pilot project for Blossoms works, maybe in a few years, we would invite you and your teachers and others to co-invent these modules and upload them onto an MIT website, which we would check for the accuracy and everything, and then put it on there so the world could co-invent these things and co-use these things. So we're looking for quality teachers from around the world. Here on your screen right now, you see Professor Walter Lewin, who is very famous worldwide for his 100 video lectures that are on MIT OpenCourseware. And soon we'll be showing these lectures live on Pakistan Virtual University. And he is one of those people who has made one of the first Blossoms modules. So if you imagine students who are in a high school here, who are age 16 or 17, who were studying Newtonian mechanics, basic physics, okay? Now, Professor Lewin doesn't open this module saying, oh, now we're gonna have a lecture on Newtonian physics. First we start with F equals ma and blah, 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 blah. No, he starts with a video of a figure skater on ice, an ice skater who starts spinning around slowly like this on the ice. And then if you notice, those of you who have seen competitive ice skating on television, you notice that as an ice skater is going like this, as she pulls in her hands, she goes faster. And there's no force on her legs. She just goes naturally faster. So Professor Walter Lewin, Blossoms module starts with that. Why does the ice skater go faster as she pulls in her arms like this? So it's a compelling question. It's to get the students involved. Now, we're hoping that 15 modules will be made here in Pakistan, 15 Blossoms modules will be made in Jordan, and 15 at MIT. And we have partners here in Pakistan, such as Pervez Hoodboy, who's a very famous physicist here. And we're very hopeful that we will have him produce at least one Blossoms module. Now, we've done research, applied research, trying to figure out what works and what doesn't work when you bring technology in to enhance education. Okay, one thing that doesn't work is if you take the regular in-class teacher and put her or him aside and put all of her students in front of computers. Because then the teacher feels neglected, threatened, a little bit hostile toward the technology. So in the pedagogical model that we're using here, the teacher is just as important, if not more important, as the video teacher. The person on video and the live teacher are kind of doing a song together, a teaching song. You could call it a teaching duet. They're partners in this. Okay? So pedagogically, the in-class teacher is just as important as the video teacher. Now, what is the point of these things? Because you say, well, we have a really rich curriculum in science and math here in Pakistan, and the students are always working. They're trying to learn optics. They're learning Newtonian physics. They might even be learning calculus, blah, 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 and a lot of things. Well, we're trying to invent an environment where the students can think out of the box. They can think about, suppose they have a blank sheet of paper and a sharpened pencil, and all of a sudden there's a problem posed to them which is interesting, compelling, and not out of the textbook. It's not something they've memorized for a test. It's not chapter 3, section 2, the lecture they heard last Tuesday. It's something different. It builds on what they know, but it builds on it in an interesting way. They might have to draw a little bit of information from here, a little bit of information from there, and some intuition and insight from here, put it all together to solve the problem. Critical thinking skills. Not memorizing for a test, but critical thinking skills. That's the idea. Creative thinking, lateral thinking. Because if you think about it, those people who start companies, those people who invent things, who have patents, they're creative thinkers. Yes, they know calculus, yes, they know physics, yes, they know geometry, but they put things together in interesting, compelling ways. So that's what we're talking about. And also, the idea is that to get these students to think that learning is not something that stops when they stop going to school. Learning is a lifetime adventure. We want to get that across as well, to foster careers in math, science, and engineering. Blossoms is a project of an MIT volunteer effort that started in the year 2002 called LINC, Learning International Networks Consortium. And Dr. Malik, who's the rector of the VU, has been a founding member of LINC. LINC is a worldwide consortium of leaders in technology-enabled education who share the vision that in the future, no child, no young person should be left behind because of their place of birth or the wealth of their parents. And we have a photograph here that you can see, which are the people who attended the 2004 LINC International Conference in MIT. Dr. Malik is in this photograph. You might not be able to see it on your TV screen. I'm also in the photograph. Elizabeth Murray, who's my co-author, is in the photograph, and many others. We've had 50 countries represented in these LINC conferences. Our most recent conference was in October 2007 at the Dead Sea in Jordan and also in Dubai. And in the photograph here, you see Her Majesty Queen Rania in the center of this photograph. Two gentlemen on her right represent the Minister of Education and Ministry of Higher Education in the country of Jordan, very supportive of LINC and the Blossoms Project. Her Majesty is very supportive of this. Immediately on her left is Professor Philip Clay from MIT. He's the chancellor at MIT. He's ranked 3rd in the administration. And MIT is very supportive of LINC and the Blossoms Project. And then there's yours truly wearing a funny tie at that event. We had 525 people at the event. You see here a photograph of some of the many high school teachers. We had 100 high school science and math teachers from Jordan there. Where did we get the idea for Blossoms? The idea that you have a TV set, and it could be a 15-year-old TV set, not some fancy high-definition flat screen. It could be an old one with a VCR, okay? Well, we were in Ningxia province in China in 2004. This is a relatively poor province in China, and many of the parents are peasant farmers who live off the land, and their annual income in US dollars might be the equivalent of $300 or so. We went to some of the schools there, and these children in these unheated classrooms in late October, it was cold outside, many of them had a TV set in the front of the classroom. And we noticed that the teacher, the live teacher, would turn on the TV for a few minutes and then turn off the TV and interact with the class in a very exciting, dynamic, jumping up and down and having conversations all the time with the students. They would get to a certain learning objective, and then she would go back and turn the TV on again for another few minutes. Now, these TV lectures were set up as, regular kind of lectures. And these teachers in Ningxia province utilized them to interact with the classroom and bring quality education that the students in Beijing and Shanghai benefited from into this poor community where they couldn't afford these world-class teachers. And still, the students there, sons and daughters of peasant farmers, got the same quality education as those from the richer cities in China. So the design features that we think are important in creating interactive video Blossoms modules are the central role of the in-class teacher, and not the need for computers, but we can have old-fashioned TV sets and old-fashioned videotape recorders. Co-creation and co-usage. We want Pakistan and Jordan and the US to be co-equal here, each producing 1/3 of the Blossoms modules in this pilot project. And then ultimately, us testing them in a small number of high schools in each of the 3 countries next year. Okay, and we want the content to be relevant locally here. So we expect that the Blossoms modules that we create in Pakistan might be quite different than those we create in Cambridge, Massachusetts, or in Jordan. But we all want to benefit and share from all of these. So we have the central role of the in-class teacher. That's very, very important. We want that teacher to be an advocate, a strong advocate, not kind of opposed to this technology-enabled education. So how do you think of this video? This video is not a lecture in the standard way, okay? This video goes for 3 or 4 minutes and then off to the in-class teacher and the students who are going to interact. So I think of this as a sandwich, which is a tall sandwich layered. The bread layers might be the video segments, and the meat and the chicken and the fish layers might be the in-class teacher. So you can think of this visually as a tall sandwich. High tech, medium tech, low tech, if we do that, so that ultimately you don't have to go to an internet cafe or have broadband accessibility to look at streaming video. We hope to be able to, and we plan to, and we have budgeted to deliver these to high schools, to deliver these modules to high schools in videotape format or DVD format, or should they have a computer, they can access it by computer as well. Hopefully that way we allow access to this material to a much broader population than we would otherwise. Co-creation and co-usage, we've talked about that. Nabil Sabri, who's from Egypt, who's very famous in articulating the views of what works and what doesn't work in developing countries. It says, among other things, we should be able to use low tech, and he also says, we want to be co-creators. We don't want all information, all educational information to come from, let's say, just MIT, for instance. We want to create an equal amount of that ourselves and share it with the world. And there he is in a picture. You might see that picture of him on the screen at the 2007 Link conference at the Dead Sea, articulating that. So our partners are Pakistan and Jordan. This is a 2-year pilot project. If successful, we're going to test it next year in some of your high schools, particularly in the Lahore region, preferably public high schools, but maybe a couple of private ones as well. And if this is successful, we're going to try to expand this and create more modules and test it more thoroughly in more high schools. And if that's successful, then we hope to implement this in an ongoing, sustainable way, kind of like what MIT's OpenCourseWare is today. We have other countries, partners in other countries who would like to join us, and we hope to add to the country list at our next round. And students also can make modules. The modules don't have to be created by professors at universities. They can be created by students at universities and colleges. They can be created by high school teachers themselves. They can be created by you. You might have a particular idea that you say, this is an interesting application of the Pythagorean theorem to design bridges across large rivers. And I'd like to tell the students about this and do it in the sense of a puzzle so that they can see that some of the things that they learn in geometry are relevant to people who design bridges. If not bridges, buildings or something else. So we had a contest at MIT recently, and we had 7 finalists. And very recently, we had the finalists come and act out their Blossoms modules. We selected 2 winners. And the MIT students are very, very excited about creating these modules. So students get very excited about doing this. They get very happy. And sometimes, I think students might be better than us professors. Us professors are not the youngest people in the world. And we're kind of removed from knowing the complexities of learning new concepts, when you're young. But the students, maybe just a few years ago, learned these things for the first time themselves. So sometimes I think the students are better teachers in these Blossoms modules than us professors are. And that's what we hope to do, is to involve the students. Now, so far, we have 5 modules created by MIT students, and these modules are the so-called 7 Bridges of Königsberg problem. And at the end of my little talk to you today, you'll see a few minutes of the 7 Bridges of Königsberg problem done by one of my doctoral students at MIT. Her name is Karima. She was born in Russia, moved to the US at age 10. She's now a US citizen. And she's working with me on doctoral research. And you'll see a few segments that she has done. We have another MIT student, doctoral student, who recently graduated with her PhD. And she did hers on fractals for high school students. We have another student who's doing one on approximations. Another on the flaws of averages. You might have heard of the law of averages. This is the flaws of averages. And then one on cryptography, kind of how to keep secrets from people and communicate with your friends. Okay, so if you think about, you might have a favorite teacher that you know in a local high school. You might be a teacher yourself or a professor. And you might be thinking, I want to participate in that. Please, if you're at all interested, send me an email, rclarson@mit.edu, and we'll communicate directly about it. But if you're thinking about creating a Blossoms module, you can go to our website, and the website will be shown in the lower part of your screen right here. And you think about, first of all, the concept. What is the concept you're trying to develop? Okay, is it designing this bridge with the Pythagorean theorem and other elements of geometry? So the concept should be of interest to students, should be exciting, and not out of a textbook. Not out of a textbook. It's not part of the regular curriculum. It builds on the curriculum either in the application area, the theory area, or a whole new combination. So you can't say, oh, this is math, or this is physics, or this is chemistry. Maybe it's a combination of these things. Okay, so not part of the regular curriculum. And it should involve a new way of thinking of things. Develop critical thinking skills. Remember, one of the things we want to do is we want to reduce the value put on rote learning, on memorized learning. We want to enhance the value placed on critical thinking. So faced with a new problem, you haven't seen it before, it's not in a book, hasn't been in a lecture, how do you frame that problem? How do you formulate that problem? How do you attack that problem and ultimately solve that problem? Those are the skills. So critical thinking skills. Another thing that's very, very hard for at least us professors who've been doing this for many years is we're used to giving lectures. I mean, I guess what I'm doing here today, unfortunately, is giving a lecture to you. And I apologize if this is a one-way thing. I'd like to have real-time dialogue with you, okay? But we're used to giving lectures. We're not used to giving 3 or 4 or 5 minutes and then stop and designing it so the next 3 or 4 or 5 minutes is out of our control. It's totally in the control of the high school teacher and her class and her students, or his students. So when you create a Blossoms module, you're doing this teaching duet with a teacher you'll likely never meet in your life, with students you'll never meet in your life, and perhaps it'll be in a language you don't understand either. We're planning on translating all the Blossoms modules into Urdu and Arabic and English. So they'll be available in the 3 different languages. But the key thing is, how do you design this so that half of the time the control is in the hands of the in-class teacher and her students or his students? The other thing is, remember that we would like these Blossoms modules to be applicable in poor regions of China or Africa and other places. And so if you need any special equipment for the students and the teacher, it should be readily available and inexpensive. Readily available and inexpensive, not fancy things. And also, we're encouraging people who make Blossoms modules not to use a lot of fancy computer graphics and all kinds of other things that only a few studios and a few people around the world have. We're encouraging, use a blackboard. Go outside. Climb a mountain. Make the module that way. Okay, so some of the concepts we have created here already at MIT is designing simple mechanisms by a professor of mechanical engineering, Professor Dan Fry. As I said, Karima, 7 Bridges of Königsberg problem, which you'll see a few minutes of momentarily. I did one called the broken stick problem, and actually the first time I did this on video, I did it here in this studio in Lahore, Pakistan. And we had a set of props here, and basically the issue was this. I had a yardstick. We have a yardstick, and we generate two random numbers on this yardstick, uniformly, independently distributed between 0 and 36 inches. And in the first segment of my Blossoms module, I say to the students, how would you generate random numbers? If you want to generate something which is uncertain and equally likely to be 0, a half, 1, 13.5, whatever, how would you do that? And then I give it off to the students and the teacher, and they talk about it for 5 minutes. And then kind of they're engaged. And then we come back, and I say, okay, we're going to generate together two random points on this. I'm going to mark them with chalk on this stick. And then I take out a saw from behind here, and I saw this yardstick, I destroy it. I saw it into 3 pieces, non-equal length pieces. And then I put those pieces together, and sometimes with those 3 pieces I can form a triangle, and sometimes I can't. So then I asked the students and the teacher, I said, if I were to do this 10,000 times, about how many times do you think I could form a triangle with these 3 pieces I obtained, and how many times could I not? And that's the problem. We solve it. It's basically for students who are taking a geometry class, which is like the science of triangles. But here's a triangle which may or may not exist, and the outcome is uncertain. So we bring probability and uncertainty into their lives. They haven't seen this before, but we enhance their curiosity and their confidence in their knowledge because we solve this together in a 1-hour session. We have this massive tree, spinning ice skater, all kinds of other sample concepts. In Jordan, I'm showing you on the screen now. On Jordan, you can see the topic areas that professors and high school teachers are currently creating for Blossoms modules in Jordan. In the next few months, we'll have a set of concepts and topics for Blossoms modules from Pakistan, and we're very happy and pleased about that. After you get the concept, then if you're thinking about creating a Blossoms module, the next key thing is the architecture of the whole module. How many segments are you going to have? How long is each segment going to be? How many different topics do you have in each segment? How many different concepts? You shouldn't have more than 1 or 2 per segment. Then let the in-class teacher go with his or her students and to talk about it. So designing the architecture is also important. Those are the 2 key things, the concept and the architecture. And after that, it's just a matter of production. And so the matter of production, if you go to our Blossoms website, which again is shown on the screen here, we actually have a 20-minute help video, tips on creating a Blossoms module. My colleague, Elizabeth Murray, is one of the people you'll see on that video. I'm on that video, and also my student Karima is on that video, because since she made one early on, and she's a student, she can give the student's perspective of what's easy and what's hard about making a Blossoms module. So if you're ready, let's phase out of this phase of this conversation, and we'll be showing you now a few minutes of Karima's Blossoms module on the 7 bridges of Königsberg problem, which then leads to the so-called Chinese postman problem. And again, thank you so much for spending some time with us today. I really appreciate it. So long for now.
Hello, and welcome everyone. My name is Karima Nigmatulina, and I'm a doctoral student at the Massachusetts Institute of Technology in Cambridge, Massachusetts. I'm excited to tell you today about a branch of mathematics called graph theory. You probably haven't heard about it before because it's not really algebra, and it's not really geometry, and it's not really arithmetic. It's something completely different. But it has many, many applications and is very useful, so I hope you enjoy the lesson. Let's start back in the beginning where graph theory was born. We have to take ourselves back to the 1700s to the city of Königsberg. Königsberg was a wealthy trading city in Prussia. And you can see on your screen right now a map of the city of Königsberg from that time. Königsberg was divided into 4 parts by a river called Pregel. The top part of the city was called Altstadt. The middle island part of the city was called Knapphof. The lower part of the city was called Vorstadt. And the right middle part of the city was called Lomsey. These 4 city parts were connected by 7 bridges. And the bridges are shown in red on the diagram that you can see here right now. So here is what the city of Königsberg looked like in the 1700s. So the citizens of the city really enjoyed their city, and they would walk around the city a lot. And they created a game for themselves. The game was, could they start in one part of the city, walk around in such a way that they'd cross all the bridges exactly once, not more, not less, and come back to that original spot where they started. So the citizens of Königsberg weren't able to come up with such a route, but they didn't know if they just couldn't do it or if such a route didn't exist. And this is the problem that we're going to start with today. Do you think that such a route exists? Can we start in one point of the city, walk around, cross all the bridges exactly once, and come back to that original starting point? Take some time with your teacher, see if you can come up with such a route, and if you think that you can, or if you think that you can't, please let me know, and you'll tell me in 5 minutes. See you soon.
Well, you've just seen segment 1 out of a multi-segment, 7-segment Blossoms learning module done by my doctoral student Karima. And you notice the segment was short, just a few minutes, and it started with an applied problem. In other words, an ancient city that had 7 bridges, connected islands and peninsulas and these sorts of things. And it asked the students to think about this and to think about, is there a way we can design a path that starts at one place in the city, goes over each bridge once and only once, and ends up back where you started? Now, if this were a traditional lecture, this might be a lecture in college or university on graph theory. And they say, well, let's imagine a graph. It's a collection of nodes and links and blah, 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 and we're going to prove some theorems about it. But see, this doesn't start as a lecture in mathematics. This starts as an interactive learning episode, exploratory episode for students and their teacher in their classroom. So after this first segment, the idea is for some of the students to come to the blackboard at the head of the class and attempt with chalk right on the blackboard, using a map of that city, Königsberg, to try to construct the path that's desired. And maybe 3 or 4 or 5 students will do this, or maybe the students will be assigned in teams and try to do this. And after about 5 minutes, they're going to be very involved in the project, very concentrated on this problem, and they're going to find out that it's impossible. They have been unable to design such a tour. So now they're committed to this. They say, this is very interesting, and somehow I can't design a path that starts and stops at the same place in the city and goes over each bridge just once. So that's the idea, to draw them in, to draw in the students, the teacher, into this problem. So now let's go to segment 2.
Welcome back, everyone. Were you able to come up with such a route around Königsberg? Well, luckily for the citizens of Königsberg, they had a very brilliant mathematician who helped them out and solved this problem. His name was Leonhard Euler. Now, probably the first approach that you took to solving this problem was you decided to go through and figure out all the different routes possible through our city. You probably started in different places and then just routed through. Now, that is an approach that would work if you could really go through and enumerate every single route. But think about what would happen if the number of bridges that we had was much more than just 7. What if we had 20? What if the number of land masses that we had was more than 4? In that case, this problem becomes, this whole enumeration becomes really, really tedious. So Euler was actually much more ingenious than that. He came up with a completely different approach to that problem than the enumeration one. So this is what he proposed. He proposed that every single landmass be represented as a node. And the node would have a capital letter attached to it to represent that node. Now, in addition to landmasses, we have bridges, right? And the bridges would be represented by arcs. And those arcs would have a lowercase letter represent them. So we have capital letters, nodes, which are landmasses, and we have bridges, arcs, lowercase letters. Now, how would we represent Königsberg in this case? Well, we would represent Königsberg as such. We have 4 nodes with capital letters, A for Allstadt, K for Kneiphof, V for Vorstadt, and L for Lomsey. And then we have 7 arcs connecting these landmasses, connecting these nodes, and those represent the 7 bridges in the town of Königsberg. Now, one thing that we can do about this is we can represent this as graph. So this is a graph. Now, graph theory says that we have nodes, as we said, and we have arcs. What are the different nodes that we have in Königsberg? Take some time to think about it. Talk to your neighbor. What have you come up with? You probably came up with nodes A, K, V, and L. Now, in addition to nodes, we have arcs. What about the arcs? What are the different arcs that we have in the city of Königsberg? Talk to your neighbor again. Come up with the different arcs. Hopefully, you were able to come up with arcs A, B, C, D, E, F, and G. Now together, the nodes and the arcs represent a graph. And oftentimes the notation that we would use for a graph is along the lines of G, which stands for a graph, is composed of nodes and arcs. So this is your first taste of graph theory. Now the observation that Euler made is really an ingenious one. He used this graph and said, well, first of all, let's look at all the different nodes. All the different nodes have a different number of bridges or arcs attached to them. We can call this number of bridges a degree. So the degree, for example, of node L is 3. We have 3 bridges coming out or attached to L. What about for node K? What's the degree of node K? Now that you've probably figured this out on your own, but just to make sure, the bridges that are connected to node K are D, E, F, B, and A. That's 5. 5 different bridges, so the degree of node K is 5. The really brilliant observation that Euler made is if every single node within the graph has exactly an even number of bridges or an even degree, then and only then will such a route around the city exist. So now that you have that observation, now that you know that you need an even degree for every single node, you should be able to figure out whether Königsberg does or does not have such a route around it. By the way, such a route, in honor of Euler, is called an Eulerian tour, or sometimes an Eulerian circuit. So that's the first thing that I want you to look at with your teacher. Does an Eulerian tour exist around the city of Königsberg? And number 2 is I have a bit of a challenge for you. What do you think would happen if we could start and end our tour in 2 different places? Does the city of Königsberg have such a path that would start in one place, move around, cross all of the bridges exactly once, and end up in another place? Think about it, and I'll see you in a few minutes.
Okay, now you've seen the second segment in this Blossoms module on the 7 bridges of Königsberg. And here now Karima has translated the problem that was originally stated as 7 bridges and a family making a walk on a family day into a mathematical problem. She's reduced it to graph theory, where a graph is a collection of nodes and a collection of arcs. And she introduced Euler's observation that for such a path to exist, that you could cross each bridge once and only once, the degree of each node must be even. That is, the number of bridges coming into that node must equal the number, must allow an exit from that node. So if you have, let's say, 4 bridges coming into a node, you can get into it once, out of it once, into it again, and out of it again. So if you have an even number of bridges, if the degree of the node is even, then a path like that can exist. Otherwise, it won't. So now, the teacher, when interacting with the class in this segment, could start off easy and say, well, does such a path exist now, an Eulerian circuit, that we're looking for in the city of Königsberg. And the students would say, well, no, it can't exist because of what Euler said. We see that some of the nodes have odd degree. And so when some of the nodes have odd degree, we know that such a path does not exist. So that's the first level of understanding here. But then the teacher might guide the students into a second level of understanding. Why did Euler come up with this? Why does this make sense? And it makes sense because of what we just said. If you have an even degree in each node, then each time you get into it, you can get out of it. Each time you get into it, you can get out of it. If you have an odd degree, then eventually you're going to check off all of those, but you get into it one time and then there's no path out that you haven't used before. Okay? So at a higher level of abstraction, the teacher may guide the students into really understanding what Euler said. And then another thing about Blossom's modules is sometimes we have little extensions, or little mind expanders. And at the end of this module, Karima said, well, okay, what about an Eulerian path? Could you start at one place in the city, cross each bridge once and only once, and end up at a different place? Now, depending on what the teacher wants to do, the teacher could really get into that extension and say, well, how might that work? Suppose you only have two nodes which are odd degree and all the other nodes are even degree. She might then guide the students, or he might then guide the students to thinking, suppose we start at one of the odd degree nodes, go over each of the bridges once, and end up back at the other odd degree node. It turns out that if you have only two odd degree nodes and every other is an even degree node, an Eulerian path does exist. So the teacher has a lot of flexibility as to the depth of conversation and interactivity with her or his class following segment 2. Okay, we're not going to show you the other segments. You can go to our website and see all the segments. But I would like to say that at the end of each Blossoms module is perhaps the most important segment. For those of you who are teachers, okay, the video teacher, Karima in this case, has a private conversation with you called the Video Teacher's Guide. In the Video Teacher's Guide, we talk about what the prerequisites are for this module, what the learning objectives are for this module, if there's any special equipment that's needed, what might that be, and maybe the approximate cost. Hopefully it's not very expensive. And then most importantly, our video teacher helps the live in-class teacher saying that how they could run each of the breaks between segments, what the learning objectives are with the class between segments. Okay? So that's the way we do this. And the Blossoms module class would be quite different than most lecture-oriented classes because it's very interactive, the students talking amongst themselves, the students talking to the teacher kind of guiding the conversation. So we're going to conclude today, and I'm going to sign up and say so long, but we're going to conclude today by showing you the first 2 or 3 minutes of Karima's Video Teacher's Guide. Again, thank you so much for spending time with us today, and I hope to hear from you by email, rclarson@mit.edu. I welcome all inquiries. Thank you very much.
Hello. First of all, let me thank you for agreeing to do this, and I hope you enjoyed this lesson plan as much as I enjoyed creating it, and hopefully your students enjoy it as well. And what I'm going to try and do right now is I'm going to try and explain what I had in mind for maybe some of the pauses in between the different sections, and hopefully this will help you out in terms of leading the class. Okay, first of all, the material that we're going to cover within the whole lesson is called graph theory. It's a sort of new branch of mathematics for probably most of the students. It doesn't really have that many prerequisites in the sense that it doesn't require any complex algebra or any complex geometry. More or less, it just requires a little bit of arithmetic and a little bit more of an understanding of what happens in mathematics, a little bit of mathematical intuition. So it's probably a good fit for anyone in high school. And furthermore, what I'd like to add is that this lesson plan really has 2 parts to it. There are 2 problems that I go through. There's the Bridges of Königsberg problem, and there's the Chinese postman problem. And it's up to you and up to the students and however you see fit. You could either have this done on 2 separate days and just do one section on day 1 and another section on day 2. Or you could just decide to push right through the whole class, but in that case it might be a little long, and maybe we can make the pauses a little bit shorter, but it's really up to you and you can make that decision. All right. So within the first pause, after I introduce a sample problem, which is the 7 bridges of Königsberg problem, usually the best thing to do with the students there is to try and give them some time with the graph, with a picture of the map, and see if they can come up with a route around the city that will take them and cross every single bridge exactly once and finish and start in the exact same place. After giving what I had in mind, maybe you could divide up the class into 4 different groups, and each group could start in a different part of the city, one in Alstadt, one in Lomsey, one in Vorstadt, one in Kneiphof, and just make sure that that way they have a better sense that all the different locations could be a starting point. And after that, after giving them a chance to really try and come up with a route, the other thing that you could do is you could have the students take a vote and vote on whether they think it's possible or whether it's impossible, whether such a route around the city does or does not exist. So that was my general idea for pause 1.